Next, we were asked to show the following inequality. If U is a solution of this weak formulation, then this inequality holds. And this can be, we are asked to show this by using the minimum problem above. We also express that this is a more difficult task than the other tasks. No, we know by the minimum formulation that f of u is less than f of phi for every phi. So what we are doing now is just to put phi equal to 0. It's not easy to see that this will give us the solution, so we that's the difficult part, just to find the value of phi for which this inequality turns into this inequality. But it turns out that if phi is equal to 0, then we obtain this inequality. This is just this f of u, and this is f of phi, where phi is equal to 0. So when taking the partial derivative of a constant, we get 0. Partial derivative of the constant with respect to x2 here, we also get 0, and this is also a 0 value. So the right hand side here will be a 0. So then we get this equation, and putting this integral on the right hand side, we immediately get this inequality. So then this is proved. Next, in the task E, we are considering a finite element problem. We'll let TH be a triangulation illustrated in this figure. So we see this is a little bit simpler triangulation than the one we considered on the lectures. So we have 4 node points, and therefore we only need 4 basis functions. And we are going to the basis functions are exactly as in the lecture, and we are going to describe how we can find an approximate solution UH in this finite element space, which is an approximate solution of the weak formulation. And this is done exactly as for the problem we have discussed on the lectures. In this case, we only need 4 vectors to describe any general solution, and the general solution is UH equal to xi1 v1 plus and so on up to xi4 v multiplied with v4, where xi1, xi2, xi3, xi4 are real numbers, and these are the basis functions associated with the 4 nodes. So then we obtain this xi is a vector consisting of these 4 components, and A is 4 times 4 matrix with elements given by this, and B is this vector of 4 components, L of V1, L of V2, L of V3, and L of V4. So we are going to, in order to compute this finite element solution, we have to compute all these values first. Next, we were going to compute the element of the stiffness matrix A of 1, 1, A11 and A12, or not 1, 2 but A23. And the way of doing this is exactly as in the lectures. We make some table here of the partial derivatives of the basis function v1 with respect to x1 and x2. We use linear elements on each of these triangles, and in this case the partial derivative in this triangle 1 is just equal to 3. The reason for this is that we have the length here is, as in the lecture, is 1, and the length here is 1/3. So when the basis function is 1 here and 0 here, we have that the derivative, the partial derivative in the x direction, must be 1 over this length, which is 3. And this is exactly as we did it in the lectures, with the only difference that in the lectures we had a different triangulation, so that we got 4 on all these places instead of 3. So the general formula for the coefficients, the capital A ij coefficients, are like this. Here we just use the general theory, and we obtain this integral. Note that the area of one such triangle is 1 over 18. That is because this length is 1/3, this length is 1/3, and in order to find the area, we multiply these values and divide it by 2. So now when we have this integrand, we note that this integrand is constant in each of these triangles separately. So we have to compute these values in each of the integrals, in each of the triangles, and then sum all these values. Don't forget to multiply with this area in order to find the integral of over one such triangle. So if we start with the first triangle here, and we know that we have this 4, the number 4 should be multiplied with the value of the partial derivative of v1 with respect to x1, which is equal to 3 according to the table, multiplied with the partial derivative, the same derivative. So we have here 4 times 3 times 3 plus, and now we come to this term, 2 times this value, which is equal in this triangle, is equal to 0 here. The same for this value, this derivative. So then we get 2 times 0 times 0. So now multiplying with the area 1 over 18, we obtain the integral over this triangle. And then we have to compute all other integrals in the same way by using this table. And doing this, we obtain that this integral is equal to 12. So then this is okay. This parameter a of 2, 3 is really simple to calculate because the supports of the base vector v2 and the support of the basis vector v3, they are disjoint. So the basis vector v2 has node point here, and the basis vector associated with the node 3 has its node point here, and the supports are disjoint. So we can conclude that this value must be 0.